All right, believe it or not, we're on the home stretch. The next section is taking a look at the redox reactions, the standard reduction potential for electrochemical cell, and free energy. We basically know that for free energy, anything where delta G is negative means spontaneous, and we know that anything with a positive potential, electromotive force, EMF, or reduction potential for the cell is going to be spontaneous as well. So these two things must be related somehow. So it turns out that the Gibbs free energy is related to the potential of the cell through this equation here. Not a big stretch for us. We know that, so delta G is our free energy over here on the left. Over on the right, we know that as the potential gets larger, it would become more spontaneous. So it doesn't make sense that those two be proportionate. And N is going to stand for the number of moles of electrons that are transferred according to the balanced equation. The negative, of course, makes delta G negative for us if the potential of the cell is positive. And F is what's called Faraday's constant. Faraday's constant has a value of 96,485 coulombs per mole. It's basically the charge on 1 mole of electrons. Remember that 1 electron had a charge of 1.6, or has a charge of 1.6 times 10 to the negative 19th coulombs. And so if you multiply that times a mole, Avogadro's number, you end up with this many coulombs per mole being equal to 1 Faraday. If we take this equation at standard state, we get delta G equals negative N times Faraday's constant times the standard potential for the cell. Now remember, we also had a relationship for delta G and KEQ. And we said that delta G was equal to negative RT ln of K. So if you go back and take a look at our thermodynamics chapter, remember that at equilibrium, the non-standard delta G would be 0, and so we get this equation here. Well, obviously, if we put those two together, we end up with negative RT ln of the equilibrium constant is equal to negative N F times the potential, standard potential for the cell. What this does is it allows us then to actually determine either the equilibrium constant if we know the standard potential for the cell, and likewise, if we know the standard potential for the cell, we can work and figure out the equilibrium constant. And of course, these are for a given temperature. But of course, very, very useful equations for us. So that's it. So we'll just practice a couple of these, and then we'll need to move on to what happens at non-standard state conditions in our next segment.